Bismillahirrahmanirrahim. Good morning to all students. I hope all of you are doing fine and staying safe. Today, our topic is going to become logic circuits. In our previous topic, we discussed about the identities of Boolean algebra. I encouraged you to solve those identities, prove them using the truth table in your own time. We did three of them in our lecture. Today we are going to explore logic circuits, and our main focus would be the half adder and full adder circuit. You might remember in our previous chat we discussed half adder circuit a little bit, and I told you that a half adder circuit is a fundamental circuit which is actually used for addition. Since one of the primary functions of a computer is to do binary addition, we can use a half adder circuit for that. A half adder circuit would give us an output in two forms, a sum bit and a carry bit. When we are adding multiple bits together, a carry bit uh, can be generated. We cannot ignore that chance. The half adder actually produces a sum and a carry bit. Let's explore that idea with the help of a truth table. Now, in my input section, you can see that we have two columns, and in the column A we have two zeros and two ones. In the column B we have a 0 and a 1 and a 0 and a 1. We also know how to fill the basic input columns. Since our O-level classes we have been making truth table, and the function behind the truth table is simple addition, and the output is distributed into two columns. One is sum and one is carry. So in the first row the both inputs are 0, so we are having sum and carry both as 0. In the second row, we have 0 plus 1, so the sum would be 1 and the carry would be 0. And the third row, we have 1 plus 0, so the sum would be 1 and the carry would be 0. In the last row, you can see that we have two ones, and adding 1 and 1 makes 2. And when we are having this situation, the sum bit would be 0 and a carry of 1 would be generated. This is why we had to make space for the carry, and this is why we had to calculate the carry as we are doing the binary 2-bit addition. Moving along, if we explore that in forms of diagram, in the previous diagram, let me show that again. In the previous diagram, we can easily see that this column is actually representing A XOR B, because when we are having same inputs, we are having 0, and we are only having 1 when we have different inputs, when we are having alternating inputs. So this column is actually made up of A XOR B, and the last column, this one 0001, you can easily see that this is an AND function. So this column is actually made up of A and B, because 0.0 is 0, 0.1 is 0, 1.0 is 0, and only 1.1 is 1. So this is how we can represent our sum and our carry bits in form of logical expressions. The sum is A XOR B and the carry is A dot B. If we make that into a diagram, the diagram representation would be something like this. A XOR would be pointing to sum and A dot B would be pointing to carry. We can also use the NAND gate diagram. We can also represent a half adder circuit in terms of NAND gates only. And we have learned to do that in our AS syllabus. You might remember the notes which showed how to represent each and every gate using NAND combination of NAND gates or a combination of NOR gates. So we just replaced the XOR part and the AND part with NAND gates, and basically this NAND is the representation we like to physically have in our computers. But when the several bits are going to be added, we might need to add the carry from the previous edition into the next edition. We might need to carry forward a carry from previous edition to next edition. So that carry is going to be a carry in, and that addition can also result in generating another carry. So that carry can be carry out. For example, let us consider this. Let's consider this addition example. If we add this 1 and 0 is 1 and 1 1 is 0, but a carry is generated. So that carry is the carry in for this addition. And when three ones are going to be added, because when we are doing 2-bit addition, the maximum inputs we can have is 3, because a carry from previous edition can be forwarded to the next edition. So when these are added, it is going to be 1, and this is the carry in from the previous edition, and the carry generated from this is going to be the carry out of this edition, which has to be added into the next column. And this is where how we actually complete our addition. Now, when we are doing this on paper, we don't realize how important this carry in and carry out is. But this little exercise can easily tell you that half adder circuit is not sufficient to do all the additions, because it might generate a carry out which has to be the carry in for the next addition. So for that we have to combine two half adder circuits and make that into a full adder circuit. So as we know that the several bits can generate the carry in and it has to be added in the next edition. The carry from the previous edition has to be added in the next edition. So this is the primary reason we need to make a full adder circuit by combining a half adder circuit. You can pause the video and read through the material. When you're done, you can play it. Now let's explore the possibilities with the help of a truth table. In the input section, I have an A and B and a carry in, and the output section, I have a sum bit and a carry out. The names are important because the diagrams and expressions are going to be proved using these names. So in the input area, the rule is still the same. We have three input uh, variables. So that means we will have to make 8 rows. 2 raised to power 3 equals 8. The first column is having 4 zeros and 4 1. The next column is having 2 zeros, 2 1s, 2 zeros, 2 1s. And The last column have 0 and 1, 0 and 1, 0 and 1, 0 and 1. The operation is again a simple addition. In the first row we have 3 zeros, so there is only 0 sum and 0 carry out. In the next row we have 2 zeros and a 1, so we have 1 sum bit and a 0 carry bit. In the third row we have again a single one, so it is going to remain the same as the previous one. In this row we have two ones, so we have a 0 in sum bit and we have a 1 in the carry bit. In this row we again have the same case of having a single one. This third last row have two ones, so there is a 0 in sum and there is a 1 in carry. The second last row also have two ones, so there is a 0 in sum and a 1 in the carry. And this last row have three ones, so it is going to have a 1 in sum and a 1 in the carry out. This truth table is fairly simple, and I know that all of you are understanding it well and all of you are able to make it without any help on your own. Now let's try to break the full adder down and try to represent it as a collection of half adder circuits and then try to deduce the Boolean algebra logical expression to represent our sum and our carry bits. So this is actually the diagram that we end up having when we add the two half adder circuits. AB goes to a half adder, they generate a sum and a carry bit. That carry bit has to be carried forward to the next addition, and that addition had to be done with the next bit of the next half adder circuit. Next half adder circuit is going to again generate a carry bit here and a sum bit here, and that carry bit from the previous half adder and this carry bit from the next half adder both have to be added into uh, an OR gate in order to generate a carry out. It's a fairly simple logical explanation. But as we remember from our half adder equation that this part, this half adder is actually A XOR B. The sum bit is being generated here. The sum bit of a half adder was A XOR B. Now let's call whole part, this whole part, let's call that X. And as this line is telling us that this half adder is again generating a sum bit, but this sum bit is generated taking the output this X and this C in. So X and C in are being input into the next half adder. So following the same logic, this next half adder sum bit should be X XOR C in. Let X be the output of sum bit of the first half adder circuit. Now, if that's clear, let's move on to the carry bit part. The carry bit of the first half adder circuit, as we have established in the previous slides, is A dot B. Now, this A dot B has to be added into the OR gate here. But this A dot B is an input with the next half adder with this X. So it is going to become X dot C in. Excuse me, C in was the input here. So X is an input of this half header, C in is an input of this half header. By the same logic we did A dot B here, the next half header should be X dot C in. And by combining them here, we can have our sum and our carry bits. Let's look at them. This is the sum bit. The value of X has been replaced by its original AX or B, and this part Cn is still the same here, and X has been replaced by its original value. So the sum bit is A XOR B XOR Cin. This is the simplest representation, the simplest logical expression of the sum bit, which we have just proved with the help of the diagram over here. This portion, A dot B and X dot Cn, they have been added into an OR gate here. So we have simply written it, but as you might have guessed, we need to simplify that a lot. In our next slide, let's do that. Excuse me. Now, let's simplify the C out. In the previous slide, we have made that the C out is equal to A dot B plus X dot C in. Replace the value of X by its original value, and we are having AX or B in its place. Now, we know that AX or B can be represented like this as well. If I'm having A XOR B, it can be represented as A inverse B plus A B inverse. This alternative representation of XOR was introduced back in your O levels, but we use that in the AS as well. So I hope that you remember that well. So I've replaced this part A XOR B with its equivalent representation in terms of the basic AND, OR, and NOT gates. Now, what we are going to do next is we are going to multiply the C in, and this is the result we are having. The multiplication is done. I'm sure it's simple. I'm taking enough pauses that you process all that in your mind as you're having the live lecture. But this is the common that we took. We took B common, and inside we are left with A plus A inverse dot C in, and this B inverse A dot C in is still the same. Now why we did that? At this point I want to show you another Boolean identity which tells us that if a variable is added with another variable and its inverse, we can just simply ignore the inverse and take the result of addition only. Now I'm not going to make the truth table here and prove this identity. I'm sure you can do this, but this is a Boolean identity which I'm going to use here to simplify my expression. So remember this Boolean identity, there is an example in the book as well, which is referring to this Boolean identity. So it might come in handy when you're simplifying your uh, exam style questions as well. So the situation is same here. A is being added with C in and its own inverse. So we can simply just ignore the inverse and we can simply write A plus C in. Excuse me. Now, after we have done that, we can simply multiply B and it would be B dot A plus B dot C in. Now, now let's look at this side. We can easily take C in common here. And when we do that, inside we are left with the same situation that we just saw. That B is being added with the A and its own inverse. So by using this identity over here, we can just simply ignore the inverse and we can write B plus A. And after having B plus A, we can simply multiply C in and we would have our simplified expression of C out. If you are feeling a bit confused, I can do that step over here as well, which I have just verbally explained. What we did here is that we already had A dot B and we simplified this portion B plus B inverse A into B plus A by using this identity, which I have just introduced to you, but I know that this is not very difficult to remember or understand. So this is our simplest representation of C out. Okay. Now that we have managed that sum in its simplest form can be A XOR B XOR C and C out can be A dot B plus B C in plus A C in. We can easily represent that into a logic circuit diagram. This logic circuit diagram is showing us the end result of the truth table from which we started this discussion of full adder circuit. You can see that A, B, A and B are going into an XOR and the output of that here is going into another XOR with C in here, and it is creating a sum bit. About the carry out, we are having first of all A dot B. This is your A dot B. And then you're having your B dot Cn and plus A dot Cn, and we have actually simplified that into this diagram. You can make a more detailed one using all the logic circuits. If you make a detailed diagram here, you will end up having 5 different logic circuits, but you'll see that it can be simplified into only 3 logic circuits. Because we are already having this output of XOR here. How we actually can do that, I am leaving up to you to figure this out. It's really quite simple. You can break the diagram down and then reconstruct it. And lastly, the way we make this circuit physically in computer is by using NAND gates only. We have replaced all the circuits with the NAND gates. The equivalent representation is there. Please refer to the basic logic gate equivalence notes that that showed you how to represent every gate in terms of XOR, or in terms of NAND and NOR that we did in the AS. We would discuss memory circuits in our next lecture, the SR flip-flop and JK flip-flop. Stay safe, and I'll see you then. Allah Hafiz.